Every time you sweat in a standard cotton t-shirt, you are essentially wrapping yourself in a wet paper towel, and it's actively fighting your body's survival mechanisms.
Oh, absolutely. It's the worst feeling.
Right. Like, picture it. You've just pushed through a grueling hike, or I don't know, maybe you're just sprinting to catch the morning train.
Yeah, that frantic commute sprint.
Exactly. And you hit that point where your clothes are completely plastered to your back. The fabric isn't just uncomfortable anymore, it's fundamentally turned against you.
It's that heavy, damp, freezing cling the second the wind hits you. We just kind of accept it as this universal human punishment for exertion.
I definitely used to.
Right, but looking at modern textile engineering, it is completely avoidable. I mean, the clothes in your closet are either facilitating your body's natural cooling process or they're aggressively shutting it down.
Which is exactly our mission for today's deep dive. We are getting into the invisible science stitched right into our everyday wardrobes.
It's such a fascinating topic.
It really is. We're looking at comprehensive insights from a platform called Apparelizer to understand the actual physics of high-tech moisture-wicking fabrics.
Because it's not just about gym clothes.
Right. Going into this, I assumed we'd be discussing standard workout gear, but the sources show a massive technological leap that affects everything from, like, how we commute to how we recover in hospitals.
Yeah, the jump from traditional fabrics to engineered textiles is, well, it's easily one of the most underappreciated scientific revolutions of the last few decades.
Wait, really? A scientific revolution?
Oh, 100%. We're talking about...
Yeah, I have a really vivid memory of this, actually. Hiking in early spring, wearing a heavy cotton hoodie. I was sweating on the way up, felt completely fine, but the second I stopped at the summit to eat lunch, I started shivering uncontrollably.
I've been there.
It was awful. My own jacket literally felt like a refrigerator against my skin.
Exactly. You experienced that cotton paradox firsthand because cotton has an incredible reputation, right?
Yeah.
It's soft, breathable, natural.
Sure, it feels great when you put it on.
Right. In a completely dry environment like lounging on the couch, it is essentially perfect. But the moment you introduce human sweat, cotton's molecular structure becomes a severe liability.
The Apparelizer breakdown points out that cotton fibers actually absorb water directly into their internal structure.
Yeah, to put it in scientific terms, cotton is incredibly hydrophilic, meaning it loves water. If you look at a cotton fiber under a microscope, it's not a solid tube.
What does it look like?
It has a hollow core, almost like a microscopic sponge. So when you sweat, the cotton doesn't just get wet on the surface. It pulls that moisture deep inside the fiber itself.
Which perfectly explains the wet paper towel effect I mentioned earlier.
Completely.
Like, a paper towel is literally designed to soak up liquid and trap it. That is great if you spill coffee on your kitchen counter. But it's a terrible mechanism if the thing producing the liquid is, well, you.
And that trapped moisture has cascading consequences. First off, the garment becomes incredibly heavy.
Oh, yeah, we've all felt that.
Second, the drying speed just plummets because the water is locked inside the core of the fiber, shielded from the surrounding air. But the most critical issue is what you experienced on that hike.
The sudden freeze, the temperature regulation completely failing.
Precisely, because evaporation completely stalls. Evaporation is how your body naturally cools itself. Sweat absorbs your body heat, turns into a vapor, and leaves your skin taking the heat with it.
Okay, makes sense.
But if you have a dense, soaked cotton barrier sitting directly on your skin, that vapor has nowhere to go. You stay hot while you're moving.
And then the moment I stop...
The moment you stop, that wet, cold mass against your skin conducts your body heat away rapidly. That's what causes that sudden freezing drop in your core temperature.
Wow. And doesn't it also cause chafing?
Oh, massively. Damp cotton creates huge amounts of friction, which is the primary cause of chafing.
Okay, so I'm fully convinced cotton is the enemy of exertion. But looking at the alternatives mentioned in the source material stuff like polyester, nylon, polypropylene, merino wool, bamboo blends, these read like a chemistry and agriculture checklist.
They really do sound pretty industrial.
And I have to admit, I'm stuck on something here. If I'm wearing polyester, I am fundamentally wearing plastic, right?
Yes, essentially.
Well, a plastic bag doesn't soak up water. Water just pools on it.
Yeah.
So how is a plastic shirt doing anything but trapping the sweat against my skin? Like, how does plastic actually keep me dry?
That right there is the central paradox of synthetic performance fabrics, and it brings us to the micromechanics.
Okay, lay it on me.
You are touching on the difference between being hydrophilic, like cotton, and hydrophobic, meaning water-fearing, like plastic. To understand how a hydrophobic material manages moisture better than a hydrophilic one, we have to look past the chemistry.
So what do we look at?
We have to look at the physical geometry of the fibers themselves. It relies entirely on a process called capillary action.
Capillary action. That's the physics concept where liquid naturally moves up through tiny spaces, right?
Exactly.
Like how a massive tree pulls water from its roots all the way up to the highest leaves, defying gravity.
That's a perfect analogy.
Oh.
But consider how the tree actually does that. It's a battle between two forces, adhesion and cohesion.
Okay, I think I need a quick refresher on those.
Sure, cohesion is the tendency of water molecules to stick to each other. That's why water forms little droplets. Adhesion is the tendency of water to stick to other surfaces.
Right. Okay.
So if you have a tube that is narrow enough, the water's adhesion to the walls of the tube actually pulls it upward, and the cohesion drags the rest of the water molecules along behind it, almost like a train.
Oh, I see. So the fabric is acting like millions of microscopic tree roots.
Essentially, yes. Yeah. But here's the true aha moment of textile engineering. Because synthetic materials like polyester are hydrophobic, they naturally repel water.
Right, like the plastic bag.
Exactly.
Yeah.
If you extrude a polyester thread as a perfectly round, smooth cylinder, sweat will just sit on it. So engineers change the shape.
Change the shape of the thread.
Yes. Instead of a round fiber, they manufacture these synthetic fibers with cross-sections that look like stars or crosses or even tiny dog bones.
Wait, seriously, the thread itself is shaped like a star under a microscope.
Yeah. What's fascinating here is that the grooves between the points of that star act as microscopic channels.
Yeah.
Because the spaces are so unimaginably tiny, capillary action takes over.
That is unbelievable.
The sweat is pulled into those grooves, not because the plastic absorbs it, but because the physical shape forces the water to travel along the channels.
That completely changes how I picture this. The fabric isn't a sponge at all. It's more like a massively complex transit system.
Yes, exactly. A highway system for your sweat. The Apparelizer insights break this down into 3 continuous stages.
Okay, what's stage 1?
Stage 1 is absorption, though capture is probably a better word. The inner layer of the fabric captures the sweat right off your skin.
Makes sense. And stage 2?
Stage 2 is transportation. Those microscopic, star-shaped channels rapidly pull the moisture away from the skin and physically route it outward, right through the thickness of the fabric.
Which leads to stage 3, evaporation.
Exactly. And here is where the manipulation really happens. Once that sweat reaches the exterior of the shirt, the channels don't just dump it in a puddle.
Right, because then you'd just be soaked on the outside.
They disperse it. The fabric spreads that moisture across a massively wide surface area on the outside of the garment.
Spreading it out to help it dry.
Yes, spreading the moisture out is the key. Because the water is not trapped inside a hollow core like it is in cotton, and because it is spread incredibly thin across the outer surface, it interacts with the surrounding air immediately.
Wait, so the fabric itself isn't actually drying me. Like, it doesn't have a heating element or anything. It's just manipulating the surface area so the air can do all the heavy lifting.
That is the genius of the engineering. By pulling the sweat to the outside and maximizing the surface area, the fabric accelerates evaporation to maximum speed.
That is so clever.
It really is. This continuous cycle effectively tricks your body into feeling constantly cool and dry, even while you are sweating profusely. It is a fundamental mechanical intervention in human temperature regulation.
Wow. Just knowing that the threads are shaped like tiny stars to channel water changes everything.
It's hard to look at your clothes the same way, isn't it?
Seriously.
Yeah.
And, if we zoom out from the gym, it becomes really clear why this specific mechanism is solving massive problems across surprisingly diverse industries.
Well, the applications are everywhere.
We're obviously looking at improved athletic performance and less chafing, but the sources also dive into applications I never would have associated with sports tech.
Yeah, the ripple effects of mastering moisture management are pretty fascinating. Sportswear is the obvious driver, and outdoor apparel uses it as a literal survival tool to prevent that hypothermia scenario you mentioned on your hike.
Right. But what really surprised me was medical textiles.
Yes, that's perhaps the most impactful crossover detailed in the research.
So what does this all mean for hospitals? Because Apparelizer notes that healthcare facilities are heavily investing in activewear technology for patients. At first glance, putting a bedridden patient in performance gear feels like a massive leap. I mean, they aren't exactly running marathons.
No, they aren't running marathons, but they are facing a severe threat from trapped moisture. Think about what happens when evaporation can't occur.
They just stay wet.
Right. A patient confined to a hospital bed for days or weeks is typically lying on cotton sheets wearing a standard cotton gown.
Mm.
They sweat naturally, and that moisture gets completely trapped against their skin.
And because they aren't moving, there's no airflow to trigger evaporation.
Exactly. When skin remains damp for extended periods, it undergoes maceration. It softens and weakens, much like your fingers pruning up in a long bass.
Oh, I see where this is going.
Now, add the microscopic friction of moving against wet cotton. For a bedridden patient, this damp, high-friction environment is the primary catalyst for severe skin breakdown, pressure ulcers, and bed sores.
Yikes.
And these are life-threatening complications in a hospital setting.
Oh, wow. So by swapping traditional linens for these hydrophobic cannel-woven synthetic blends, the bed sheet itself is actively pulling the sweat away from the patient's body.
Yes, it pulls it away and disperses it to the edges of the bed where it can actually evaporate. You are maintaining the integrity of the patient's skin by mechanically regulating their microclimate.
That is brilliant.
It really is. It prevents bacterial growth, especially when they pair it with antimicrobial silver or copper treatments woven into the fibers. And it drastically reduces friction.
So optimizing a marathon runner's comfort directly translates to saving lives and improving hygiene in healthcare.
Exactly. It shows how sports tech improves general human welfare.
It really just comes down to the physics of keeping skin dry. Which leads me to ask, if we have already perfected the star-shaped fibers, if we've mastered capillary action and solved the evaporation puzzle, what is the next frontier?
That's the big question.
Like if I look at my wardrobe 5 or 10 years from now, what is this technology evolving into?
Well, the transition happening right now is moving from passive fabrics, materials that just react to sweat, to active responsive technologies.
Yeah.
The industry calls them smart fabrics.
Right. The source material describes these as textiles that maintain all the moisture-wicking properties, but simultaneously monitor your heart rate, your body temperature, and your hydration levels.
It's incredible, isn't it?
Here's where it gets really interesting, because it sounds like our wardrobes are slowly turning into wearable smartphones. Or like a second layer of skin that does the breathing for us.
A highly functional second skin is exactly how they envision it. And the way they are achieving this, without turning your shirt into a stiff suit of armor, is through nanotechnology.
Nanotechnology, so even smaller than the star shapes.
Yes. Manufacturers aren't just altering the shape of the fiber anymore. They are engineering materials at the microscopic molecular level.
How does that work?
They can embed microscopic conductive nanothreads directly into the star-shaped channels we talked about earlier.
Wait, so the sensors are actually woven into the capillary system itself?
Yes. The fabric retains the exact softness, drape, and durability of a normal shirt. But it can conduct electrical signals from your body's surface-like muscle impulses or even sweat composition directly to a tiny processor.
That is honestly mind-bending. But we have to address the massive elephant in the room regarding all of this.
I have a feeling I know what you're going to say.
Because when we listed those miracle wicking materials earlier, polyester, nylon, polypropylene, we are fundamentally talking about wrapping ourselves in highly engineered petroleum products, right? We're wearing plastic.
Yes, and that reliance on fossil fuels is the most critical challenge facing the performance apparel industry today.
I mean, every time you wash a traditional synthetic shirt, it sheds microplastics.
Exactly. If we connect this to the bigger picture, the intersection of elite technical performance and severe environmental impact is impossible to ignore anymore.
And Apparelizer specifically highlights sustainable performance materials and bio-based textiles as the industry's response to this.
You do.
But how are they replicating a star-shaped hydrophobic fiber without using crude oil?
There are two main avenues. The first is basically a stopgap, which is recycled synthetics, taking existing plastics like water bottles, melting them down, and extruding them into those specialized fiber shapes.
Okay, so that keeps plastic out of landfills, but it doesn't solve the microplastic shedding issue.
Exactly. The true future really lies in the bio-based textiles.
Bio-based, meaning they are grown, not pumped from the ground.
Precisely. Researchers are successfully extracting cellulose from renewable sources like bamboo, eucalyptus, or even agricultural waste.
And they turn that into clothes.
Yeah, they chemically transform it into performance fibers. But even more advanced are biopolymers, like PLA, which stands for polylactic acid.
Okay, what is that?
It's a plastic substitute fermented from the sugars in cornstarch, or sugarcane.
Wait, so they can take cornstarch, turn it into a biopolymer, and extrude it into those same tiny moisture-channeling shapes?
Yes. They achieve the exact same capillary action and rapid evaporation, but the base material is completely renewable. And under the right industrial conditions,